Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Nice thing is, we also have what's called virtual network infrastructure. So we just talked about type 2, and we've been talking about type 1 for a little while, but type 1 goes a little bit more in depth. Again, hardware, that's going to be the physical hardware, and then directly on top of that will be our hypervisor. That'll be type 1. That might be VMware ESXi, for example. The type 1 hypervisor will be directly installed on the hardware. This is also called bare metal. So when we are installing a VM on a hypervisor, we have to have some type of management software to be able to install that. Cisco has a Cisco Unified Computing System Manager. Windows has Hyper-V. VMware has ESXi and a web GUI. And again, there's a plethora of other versions out there. It's just these are some of the common ones. So what happens when we bring in the complexity of network virtualization? If we were just talking about all of our virtual machines and being able to separate all of the VMs, how can we guarantee traffic is actually being kept separate? So server virtualization hides server resources. This can create problems when we are designing the network. VMs are movable, and these are objects that can be added, dropped, and changed pretty quickly. So with that in mind, we have to also look at what resources on the network are going to be available. So traffic flow may differ from the traditional client-server model. So with that, we have to have a considerable amount of traffic will be exchanged between the virtual servers that can change in location and intensity over time and over a given short period of time. For example, you may have one server in one location that's pretty idle, but Monday for 4 hours that server may generate a ton of traffic. So that server now is going to consume a ton of bandwidth that normally it wouldn't. Those are some of the things that we have to deal with. So part of that will also mean the dynamic will ever be changing, and the traffic requirements have to be flexible enough to meet all of these needs. That's why we have things like QoS. However, in the larger enterprises using multi-vendor equipment, each time a new VM is enabled, they may have to be reconfigured, and that can also be very time-consuming. The network infrastructure can be benefit from virtualization, just like the actual server infrastructure can benefit. So network functions can be virtualized just like anything else. Each network device can be segmented into multiple virtual devices that operate independently of one another. We have what's called virtual routing and forwarding planes. They are called VRFs. We have our VLANs. However, with virtualization, VLANs slowly are becoming obsolete because realistically they can't keep up. In one of my other videos, I discussed VXLANs, and that's a improvement on VLANs, but that is definitely a CCNP level topic. Moving on, we have our software-defined networks, our SDNs. So we're going to be looking at network programming, looking at SDNs, and we're going to wrap it up with our controllers. So first of all, our controllers will have two main types of planes. That's going to be a control plane and a data plane. The control plane is typically regarded as the brains of a device. They do all of the layer 2 and layer 3 functioning, the routing, the forwarding, the address tables, STP, ARP tables, all of this is sent to the control plane and is processed by the processor. The data plane is also called the forwarding plane, and this is the plane that will typically deal with the switch fabric, connecting the various network ports to a device, and the network plane for each device will be used to forward traffic accordingly. Routers and switches will use information from the control plane to forward incoming and outgoing traffic appropriately. Information in the data plane is typically processed by a specific data plane processor without having to get the controller plane's CPU involved. So one area that's important to understand is that the control plane and the data plane will have additional features. The data plane may also look at the CEF. This is an advanced layer 3 IP switching technology that allows for the forwarding of packets to occur, again, at the data plane. And this is all without involving the control plane or the control plane's CPU. So basically what ends up happening is the SDN is basically the separation of the control plane and the data plane. The control plane function is removed from each device and is performed by a centralized controller. The centralized controller will communicate and it will perform the appropriate function. Each device can now focus on just forwarding data while the centralized controller will manage the data flow. So when we're talking a large level switch, you'll have controllers in there. Typically those controllers are the control plane. They are not the data plane. The individual stacks in there should have their own data plane. We also have what's called a management plane, and this is responsible for managing the device through a connection to the network. Normally the administrator will have the connection like SSH or HTTPS or maybe even SNMP. They can use things like FTP or TFTP for copying content to and from. Within our architecture, we have two main support areas for developing network virtualization. That is our software-defined networking, SDN networks, and our Cisco application-centric infrastructure, ACIs. The SDN is a network architecture that virtualizes the entire network, offering a new approach to network admin and management. The Cisco's ACI is a purpose-built hardware solution for integrating cloud computing and data center management. So the SDN can also include things like OpenFlow, OpenStack, and other components like Trill or Fabric Path or some form of 802.1AQ. OpenFlow is a Stanford University development approach for managing traffic between networking devices. OpenStack is basically an approach to virtualization and orchestration platforms designed to build scalable cloud environments. A traditional and SDN architecture. A traditional architecture will have each device having their own control and their own data plane. Within the SDN architecture, we will have a control plane, and each device will have their own separate data plane. And the nice thing with this is you can have one control plane that will manage multiple devices. The SDN controller is a logical entity that will allow administrators to manage and dictate how the data plane of switches will handle traffic. The complete SDN framework is shown in the figure next to the text. The SDN controller will use both northbound APIs to communicate the upstream application and to allow for the southbound APIs to define the behavior. Essentially here, as long as data is flowing, it's going to handle on the data plane. Anything that we're going to have to work with routing or layer 3 content, it may have to go to the control plane. Or other type of traffic engineering, again, that will have to go to the control plane. The nice thing is you can have multiple devices operating at the data plane, and they can all share one SDN-based controller. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.